First speaker for the afternoon session would be Orly Shenker from the Edelstein Center at the Hebrew University of Jerusalem. The majority of Orly's work concerns the philosophy of physics, mainly philosophy of statistical mechanics and philosophy of quantum theory. Her recent works with Meir Chemo, including their book The Road to Maxwell's Demon, demonstrates, among other things, that our understanding of the meaning of our physical theories can benefit from the study of the place of the observer as part of the physical world which the theories describe. Today she will talk about entropy, information versus probability.
Thank you, Bai. I've changed the title a little bit, information versus entropy versus probability, and I'll explain why I've done that. So the connection between information, entropy, and probability between these three concepts is created in the context of which, but as I will show today, these concepts are not identical. My product goes in a route that is very different from some of the talks that we heard today and yesterday. Namely, many people try to expand the domain of application of the term information and use it in a variety of contexts, and showing how fruitful it is, how useful it is, to the extent that it is. And we saw some criticism about this in Olympia's talk this morning. So my aim today is to show that in a context in which is taken as a paradigmatic case of the connection between these three terms, there is no such connection. So this is my main claim today. Information is not thermodynamic entropy. It doesn't entail it even. It's not even correlated with it. The same goes for probability. Now the belief, the terminological, the way we use these terms originates from some works, mainly two works that date back to 1948, which we're all familiar with. The first is Wiener's book, Cybernetics, the Control and Communication in Animal and Machine. The term cybernetics, coined by Wiener in this work, refers to self-regulating systems. And as it turned out in this book, the concept of information had a central role there in the way that Wiener understood it. In this book, Wiener claimed that information is not matter nor energy, but something else, something above and beyond matter and energy. And he tried to explain what it is and how it relates to matter and energy. One subject in this multidisciplinary book of Wiener was the idea that the acquisition of information has a quantifiable price in terms of thermodynamic entropy. The idea of that Wiener mentions is that the acquisition of a bit of information costs k log 2 of entropy increase, and he took this idea from Szilard, 1929. Other people worked further on these ideas later on, and it was changed in a variety of ways. Today, people say more that the loss of a bit of information has the price of k log 2 of information. This is the entropy cost of erasure. But I put these kinds of arguments as in one set of ideas, namely that the acquisition or loss of a bit of information has a cost in entropy. This idea is very popular, appears in many contexts, but it is mistaken. And in all of its formulations, and Meir and I proved that it is mistaken in our book. This is not the main point of my talk today. So I'm mentioning this just to say that when I disentangle information and entropy, this is not the direction in which I want to go today. The other work that is a centerpiece of our workshop today, sorry, I'm going the other direction, yes, is Claude Shannon's 1948 article, The Mathematical Theory of Communication, where he looks for optimal ways of coding messages and so on, discussing noise and all the rest of the ideas that Olympia discussed this morning. So naturally, information was a central notion in Shannon's work because non-technically, this is what we want transmitted along a communication channel. So Shannon wanted to quantify the amount of information to be transmitted and found a full formula for this. And then he received an advice by John von Neumann, who he had met several years before. And in an interview, Shannon recollects, he says, "My greatest concern was what to call it. I thought of calling it information, but the word was overly used, so I decided to call it uncertainty. When I discussed it with John von Neumann, he had a better idea. Von Neumann told me, you should call it entropy for two reasons. In the first place, your uncertainty function has been used in statistical mechanics under that name. In the second place, and more importantly, no one knows what entropy really is, so in a debate you will always have the advantage." Now this advice by John von Neumann that Shannon adopted was unfortunate and caused a lot of misunderstanding, mistakes, various kinds of errors that are still with us. So in this talk, I want to disentangle the connection between these terms, and this is just the anecdotal background of this idea. I will not go into the history of statistical mechanics when discussing this idea and when comparing information with entropy and probability. Instead, I will jump to contemporary discussions of the foundations of statistical mechanics and explain what are probability and entropy in this contemporary theory. Then we will be able to see that these concepts of probability and entropy have almost nothing to do with information, but we will also be able perhaps to understand where the mistake came from. Let's see where we are now. Yes, so the best place, the most natural place to start our talking about the foundations of statistical mechanics is the second law of thermodynamics, which says very roughly and briefly that in isolated systems, entropy does not decrease with high probability. So we have both terms, entropy and probability, within the second law. The second law is a generalization of observed phenomena. In the paradigmatic case is that of a gas in a container. We start with a gas in a container with a partition, then we remove the partition, let the gas do what it does by nature, and we know from experience that it expands until it fills up the entire container and remains in this equilibrium. This is the paradigm of the second law of thermodynamics. Daniel talked more about this law in his lecture, so I will not expand any more on this background. Now, thermodynamics is not a fundamental theory. Thermodynamics has the status, I maintain, of a special science. It is not different from biology, for example, as an important case. It is a phenomenological science, a science at the directly observable level. It discusses a concept, some of which we take to be more or less directly measurable or directly observable, as some of the notions used in biology. Not all of them in both sciences, of course, but there is a great similarity between them. And the main point of similarity, that none of them is a fundamental science, And both people that are doing biology and people that are doing thermodynamics, by and large, agree that the fundamental science of the world, the best one that we have at this point, are the theories of physics, especially mechanics, whether classical mechanics or quantum mechanics or the evolution, whatever it will be, of these theories. And here I will talk mainly in classical terms, but whatever I say can be translated or transformed or changed into terminology of quantum mechanics. I will not need the complexity, the extra complexities of quantum mechanics, so I will leave this to the side. If you want, we can talk at the Q&A session. But right now, I'm talking classical physics. So since thermodynamics is a special science, the question arises, as it arises in other special sciences, how can these phenomena be explained or derived from or accounted for in terms of the fundamental theory, namely mechanics? So we have here the standard presentation in which we have here a state space, the space, the abstract space in which each point stands for a possible state of a system according to your favorite theory. We have here in this oversimplistic depiction, we have a set of these states that we see at the phenomenological level as a far from equilibrium state. For example, this case, this is a far from equilibrium case. And then the microscopic state of the system, which is a point here, evolves in its trajectory according to the mechanical equations of motion, and it passes through a closer to equilibrium states until it reaches equilibrium and remains there. This is the mechanical thermodynamic trajectory. It's thermodynamic since it satisfies the observable properties of thermodynamics by assumption. It's not actually an assumption. There are various degrees of proof here, or of deriving the observable quantities from fundamental ones, as is known in statistical mechanics, and I will not go into these details here. So, the desideratum, the holy grail of statistical mechanics as a project. Statistical mechanics is actually a branch of mechanics, and it's a branch whose aim, whose project, whose goal is to derive the phenomenological laws of thermodynamics from the fundamental laws of mechanics. So it should be a branch, the desideratum is that the second law of thermodynamics will be a theorem in mechanics. This is what people are after. Whether or not they can achieve this is another question, but I'm just at the descriptive level of the project here. So this is what we want to achieve. But the problem is, and it is a well-known problem, that the moment we move on from the phenomenological level to the description in terms of mechanics, new options, new possible worlds arise, and this is one of them. This is the well-known case of Schmidt reversal. This is a point that was made by Schmidt already to Boltzmann in the 19th century, when Boltzmann suggested the mechanical view of the mechanical underpinning of thermodynamics. So Schmidt pointed out that for every trajectory that goes, so to speak, forward towards equilibrium, there is a trajectory that goes away from equilibrium. And the number of such trajectory segments is equal. And so the question is, how can we account for the phenomena of thermodynamics, given that these two kinds of macroscopically appearing trajectories are possible according to mechanics? And the very fact that they are possible is non-controversial. This is agreed by everybody. The question is what to do with this fact. The fact of anti-thermodynamic trajectories is an outcome of the time reversal invariance of mechanics that Gabi mentioned his brief remarks. The question is, why is this taken to be a problem? And here I will, I don't know if there are loudspeakers here, so let's try. These are our heroes to explain the problems. Let's see if they can do it. Maybe some of you know this. No, it doesn't work. So anyway, I'll tell you the story. Many of you may know this. The couple here allowed their kids not to go to school for a few days, let the kids just do what they want to do, and they're very worried about the results. The boy is doing, I don't know, flying kites at night. The girl builds a perpetuum mobile. And so you can't see it here, but you'll find it easily on the web, this clip. So Lisa builds a perpetuum mobile, and her father shows it to her mother and says, you know, what's this thing? It's going faster and faster. And they're very worried about what's going on, and so they call Lisa to their bedroom, and the father tells her, in this house, we obey the laws of thermodynamics. So this is our problem. And not because we want to obey. Actually, we would love to disobey the second law of thermodynamics. It would be great if we could do that. But we believe that in normal circumstances, generally, we can't. This is the standard approach, the standard understanding of thermodynamics, and this is why it is such an important and such an annoying law of nature. And energy is conserved, but we cannot use it. So this is the problem. How to account for the second law of thermodynamics, given that there are anti-thermodynamic trajectories. The solution, the standard solution, is well known and was given already by Boltzmann when he was presented with Schmidt's objection about anti-thermodynamic trajectories. And what Boltzmann said is that, very simply, the two kinds of trajectories are possible according to mechanics, but the thermodynamic ones are probable given the initial state of the system, and the anti-thermodynamic ones are improbable. And since then, we call this branch of mechanics statistical mechanics. It has to do with statistics. Statistically speaking, everything is thermodynamics. Of course, the probabilities are such that we don't expect to really see violations of the second law. The anti-thermodynamic trajectories are thought to have very small probabilities, almost zero probability. We don't expect ever to see them according to standard understandings of the term probability. So this is the solution that Boltzmann proposed to this well-known problem. What I would like to do at this point is to try to describe a little bit more precisely what the second law of thermodynamics says in terms of the second law of thermodynamics. I will not discuss whether or not it can be proved. I think it cannot be proved. I think there are provable counterexamples to the second law of thermodynamics. The best known ones are the family of Maxwell's demon. I think these cases that are perpetual motion machines are possible according to mechanics. They are compatible with mechanics. Whether or not we can see them around, whether or not we can build them is another question, very interesting one. The answers are non-trivial. But this, again, is not my topic today. I will not discuss whether or not we can prove the second law. Rather, what I want to do is just to describe it, because the precise description of what the second law actually says is, of course, a critical step towards proving it, or at least understanding whether it is provable or not. So this is what I'm doing today, just describing what it says without addressing its provability. So in order to understand what the second law of thermodynamics in this probabilistic version says, we have to answer at least the two following questions. Two problems with Boltzmann's solution. One is probability of what? If we have a set of trajectories that are probable and another set which are improbable, the question is exactly what is the subject matter of this probability statement. This is a question that was raised in a different context in Yamima's talk. So it will be interesting to think about the connection or disconnection between these two realms where probability statements are made. So the first question would be probability of what? And the second is, how is the probability determined? We know that in Kolmogorov's standard formulation of the theory of probability, the events and their probabilities are given. Once they are given, we can do all sorts of things with their probabilities and apply the theorems and so on. But this is a starting point that is not given by the theory of probability. This is something that we have to provide. It is part of perhaps our ontology or epistemology or what have you, according to your favorite understanding of the term probability. And we'll have more to say about this a bit later. So these are our two questions. And I'll address them one after the other. And in order to understand them, I will present very briefly and in general terms some fundamental concepts of mechanics and of statistical mechanics. Without going into any formalities, I will rely on your intuitions, mechanistic, classical mechanistic intuitions. Okay, so problem one. Probability of what? So here again is the state space of a mechanical system. Every point in this state space represents a microstate of the system. Now the term microstate has various meanings, and it is crucial to distinguish between them and to understand what I mean when I'm talking about a microstate or a microscopic state. In the way that I talk about this, which is the way this notion is used in statistical mechanics, micro has nothing to do with being small. It is not about small. It's not that a particle, an atom is micro and a billiard ball is macro. This is not what we mean by micro. It's not about smallness. It is, nor it is about the relation between part and whole. It's not that the particles that make up the billiard ball are the micro level, whatever it is, and the ball as a whole is the macro level. It's not this either. So it's not small, it's not the part-whole relation. Micro, in this technical term that is used in statistical mechanics, means a complete description. It's about completeness. When I talk about the microstate of, for example, the gas in a container in the paradigmatic example, what I mean is this. At a given point of time, and time is continuous and has points in, it's a real number in classical mechanics. So at a point of time, there is a matter of fact in the world concerning the actual positions of each of the particles in the universe, the actual velocity of each of these particles, their parameters like mass and charge, or about some external fields or fields that work between them, etc. But I will focus here on the positions and velocities and take all the rest to be parameters of the problem. So a microstate is a precise description, or not description, I can never describe it, of course, but it's a precise fact about the world. The full state of the universe, including all its particles, at a point of time. This is a microstate. This is the notion that we use in statistical mechanics, and it's crucial to bear this notion in mind when we proceed, because if we use it in any other way, we will not understand correctly the relation between micro and macro, and various kinds of errors can result from this. So I will insist on and emphasize this notion of micro. Micro is precise, full description of the state of the universe according to your favorite theory, which is right now classical mechanics. Okay, now, thank you very much. So we have at each point, according to mechanics, there is only the microstate of the universe. This is all there is. There is nothing else in the world. So what can we say more about this? We can, of course, apply the equations of motion and predict the future microstates of the world. This is one thing that we can do. But there is another thing that we can do, which is important for our purpose here. And this is describe the world only partially, not describe the full microstate of the universe at that point of time, but describe only part of that information. For example, we can describe some average position or average or the way in which the particles are spread in some part of the space. And talk just in general terms, not naming the particles, not caring about small differences in position, but something very general, and we can describe this using the terms of physics. This is just ignoring some of the information, which is in, excuse me for using this term, I'm not using it as theory of information, it's just a careless, not careful use of the term. So I'm using a partial description of the complete description or the complete state of the universe. Another famous case of a partial description is the case of the average kinetic energy of an ideal gas in a container. So an ideal gas, it doesn't matter the technical details. Think just the air might be an approximately ideal gas in a container. So if you look at the microstate of the particular air in this room and think about its molecules and their velocity, there is a fact at each moment concerning the average kinetic energy of these particles, right? We measure or we think about the kinetic energy of each of these particles. We take the average. And then we can think about various statistics that we can do about this. But it's the point is that when I'm talking about the average kinetic energy, which is taken to be the temperature in statistical mechanics of a gas in a container, I'm talking about the actual microstate of the gas right now when I'm looking at it, when I'm measuring it. No counterfactuals are involved. It's an actual fact about the actual gas that I'm measuring, because there is nothing else in the universe. There is nothing I can measure except these microstates. This is all there is. So when I'm talking about the temperature of the gas, I'm just ignoring some of the information, some of the part of the full microstate, and focusing on a partial description in which I'm interested. The partial descriptions are called, in the jargon, they are called macro variables. So this is the term. A macro variable is nothing but a partial description of the microstate. Now, if you think of a microstate of a system at a certain point of time, there are, of course, infinitely many macro variables. You can write down any partial description that you want. You can invent any function of the microstate of the system. And since the thermodynamic systems are very complex, it's very easy to come up with imaginary, useless expressions that are all of which are partial descriptions of the system. But the fact is, and this is a fact about our contemporary science and about our way of experiencing the world, we don't experience most of these macro variables. We only feel directly, and we only write about some of those partial descriptions, some of those macro variables. For example, we write a lot about the average kinetic energy, or about the volume, which is a dispersion in the box of the gas. So we are only interested in a small number of these macro variables. Of course, we can increase this number as we learn more and more about the world. I'm not saying this is a finite number, but it's not a big number. Even if you take all the kinds of temperatures in various materials and various circumstances, they have different expressions. Okay, take all of them. The number is not that big. So we don't actually care about most of the macro variables, but only about some of them. And I suggest that those that we care about, those that we write in our theories, those that we talk about even in our daily life, are those with which we, as physical systems with sense organs and brains, etc., can interact. We can relate to those partial descriptions. For example, I don't interact with all the details of the microstate of the air in the room right now. I only feel that it's a bit too hot. That's it. So I feel its temperature. I interact in ways that the biologists among you and the physiologists among you know much more about than me. My body interacts with that partial, with this property of the air around me. It's a very complex interaction, blah, blah, blah. We don't know how it goes on. Okay, but according to physics, if I take mechanics seriously, and I do right now, this is everything that there is. There can't be anything else, because there is only the microstates and its partial descriptions. So those macro variables that I can relate to, either by interaction, by experience, or in my theories, I called macrostates. And this is why I drew this eye here. So what we have here is the following in this drawing. So we have here a microstate, which has a trajectory. This is the complete state of the universe. Now, what is this set? If I describe this microstate, not in all its details, but only focus on a partial description of it. For example, average kinetic energy. If I only mention this partial kinetic energy, then there is a whole set of microstates, counterfactual ones. They're not the one that obtains right now, other ones. But the other ones are indistinguishable relative to the partial description of average kinetic energy. So when I'm talking about the average kinetic energy or other macro variables of the system, I'm talking about a partial description of the actual microstate in front of me. But at the same time, this partial description picks out a set of microstates, all of which are indistinguishable relative to this macro variable. They look the same. So they are counterfactuals, but they make up a set. And if the only thing I know about the air in this room is its temperature, then all I can do is refer to a set of possible microstates. One of them is the actual. So this set is the macro variable in the sense of picking out a set of indistinguishable microstates. And if this macro variable is one of the small set of macro variables that I can interact with or experience or talk about theoretically, blah, 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 then it's a macrostate. And this is why the I here is the role of an observer that prefers certain macro variables over others. The status of this observer is, of course, a big problem that I will not discuss today. Of course, if statistical mechanics is to be a theory of physics, the observer has to be physical, completely. Identity, reduction, all these words that everything that accept, everything that is reject, that is, everything that is not multiple realization. If there is multiple realization, then statistical mechanics will no longer be a physical theory. But I leave this to the side. Right now, I don't care if the observer is something outside my theory. It's not the point that I want to pursue at this point. So these are the microstates, the macro variables, and the macrostates, which are the sets of interest, the sets that in statistical mechanics we talk about. Now, the last term that is important for us is preparation. Suppose that I want to prepare a set, not a set. I can't prepare a set. I can prepare only the actual system in front of me. So I want to prepare a gas on this table so that it's confined to the left-hand side of the box. What I do here is actually prepare the microstate of that actual gas so that it is one of the microstates that shares a macro variable of the kind that I can relate to. And moreover, in that case, a kind that I can control. It's not enough to prepare a system. It's not enough for me to know its macro variable or macrostates. I need to control it. So I prepare a system in a microstate. Nothing, because there is nothing else in the world. But it's a microstate which is one of a set of those that share a macro variable of the kind that I can relate to, namely a macrostate. This is what I mean by preparing a system in a state. In physical terms, in mechanical terms, apart from the observer, but forget this. Forgive me for not going deeper into this point. So, when we say that the second law is about the evolution of state, the probabilities of the evolution of states, what we're talking about is the evolution of macrostates. We're saying that a system that starts out or prepared in a far from equilibrium state, microstate, which is a macro variable, blah, 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 will evolve all of them, all of the trajectories that start out from all the points in this set will have trajectories that will evolve qualitatively similar to the one illustrated here. So we know now probability of what? The probability of the microstate being in a macrostate. Yes? 5 minutes. Okay. Wow. So I'll hurry up. Okay. So this is problem one, probability of what? The second problem is how is probability determined? Now we have all the tools. Here are 2 microstates, and all the bundle of trajectories involves, and these are I forgot the word, just cutting the bundle of trajectories at certain points of time, okay? So these are endpoints at T1, and these are endpoints at T2 of the trajectories that started out here. So suppose that I calculate all these trajectories, and think of the endpoints at T1. The endpoints at T1, this bundle or these points, overlap with 2 macrostates. This one and the one closer to equilibrium. And when I say that there is a probability of evolving to say, to the second macrostate. This means that some of the trajectories will end up here, but some may remain here in this particular case. How many? Well, I will look at the partial overlap of this set of endpoints with the different macrostates. And the size of these partial overlaps will give me the probability of ending up either here or here, given that I started out here. So it's a transition probability. And now the question is, since this state space in mechanics is a continuous space, in order to say what is the size of the partial overlap, I need to choose a measure. And the idea is this, and the idea of how to do it is this. I will prepare systems, all of them in the same initial macrostates. And I will measure them. And I will see how many of them were at T1 in the same far from macrostates, and how many are at T1 at the closer to equilibrium macrostate. So I will have relative frequencies of systems in both macrostates. I will then find a measure such that if I impose this measure on the state space, the relative region, the sizes of the overlaps will be the same as the relative frequencies that I measured. In this way, I can choose a measure according to mechanics plus some observations. Now, the choice of measure here will in general not be unique, and I can choose any of the measures that will be suitable to this, that will repeat or reflect the relative frequencies. And this measure will be my probability measure, normalized, etc. So these are probabilities. And in this term, I can now say that the second law of thermodynamics is that increasingly big overlaps will be with increasingly big macrostates. This is what we see here. So here is a case of the second law of thermodynamics. At T0, everything is far from equilibrium. At T1, there is a greater probability of being closer to equilibrium. And at T2, we have a high probability of being in equilibrium. And at T3, there is no other options in this case. So we have increasingly big overlaps with increasingly big macrostates. This is the description of the second law of thermodynamics in terms of mechanics. But here, and these are my final comments here, and I think these will be easy given what I said so far. So when I say increasingly big overlaps, I'm saying that they are increasingly big according to the probability measure that generalized my observed relative frequencies. They're not a priori, they don't have to be a big measure or any other nice measure. Anything that matches the relative frequencies will work. But now there is another term, big, here. And I need to look at this one, the other one, the big macrostates. What do I mean by increasingly big macrostates? We talked about sets so far, but we didn't talk about their sizes. So normally, when we talk about the sizes of macrostates, we talk very quickly, we associate it with entropy. Big sets of microstates are sets with higher entropy. We're using the notion of typicality and so on in this context. However, when we construct statistical mechanics or the counterpart of the second law of thermodynamics from mechanics, we don't have any a priori measure. We can't use any a priori notion of ignorance and so on. We have to choose a measure according to which to determine the sizes of these sets. And how do we do this? Answer, we go to thermodynamics, to the empirical data to the phenomena. And we choose a measure of the macrostates in such a way that the result will be that increasingly big overlaps will be with increasingly big macrostates. So we have here two measures. The measure of probability determined by the generalized observed relative frequencies, and the measure of entropy determined so as to ensure matching with thermodynamics. And the question is, where is information? I didn't use the term at all when constructing the second law of thermodynamics. Of course, once I have these measures, I can use this system as a source. I have probabilities, well-defined ones. Now I can start applying the theory of information as communication, blah, blah. But this notion is just an application of things that I already have. The notion of information has no explanatory role at all in statistical mechanics as I construed it here. And this is my main point. And what I would like to emphasize now is that the thing that I'm saying about constructing thermodynamics as a special science from mechanics applies equally to other special sciences. Biology, the biological terms are macrostates in a similar way. They are observable properties associated with sets and so on. And therefore, also in biology, whether the laws of biology are deterministic or probabilistic or ceteris paribus or what have you, the only way to understand them, which does justice to the claim and takes seriously the claim that fundamentally everything is physical, is this way. And in this way, the probabilities used in all the special sciences are fully reducible to mechanics, given that probability measure is chosen this way and the measure of the relevant sets is chosen in this way, and information can be then applied but has no explanatory role whatsoever. And more details are here. Thank you very much.
Thank you for giving me a very clarifying lecture.
Now it's on.
And the criticism I'm going to give is by virtue of the assumption of characterizing classical mechanics as fundamental, or at least as part of fundamental theory as far as you. Classical physics, as you use it, has no dimensions in it. I mean, it applies to big, small, etc., etc. It doesn't describe objects. It describes parameters. There is no way it can make for compounds or except for gravitation, which has its own thermodynamic problems because it's always attractive. So, thermodynamics, as it describes phenomenologically, if you want to have a foundational theory which possibly could describe or must make use of quantum mechanics. I mean, to describe objects which automatically brings in a description between micro and macro, not in your sense, but between small and big by virtue of Planck's constant. And it's already there by virtue of talking about limits of n going to infinity, v going to infinity, n over v, so that all of these things are necessary to go from a quantum mechanical description. Quantum mechanical also gives you the connection to information, because then there is the theorem, or at least the folk theorem, which says You can simulate anything by qubits, and the qubits in turn give you the relationship to bits, which then eventually you can try to relate to information. So my criticism is, it's a beautiful lecture, and everything you say is to be taken very seriously.
Just not true.
No, it's not a question of being not true. No, it's an issue. It's again this issue of what is true. It's only true to the extent that you can prove that it's false because you give me the limitations of it.
Which is the quotation that you brought a few days ago, the beautiful one. Quantum mechanics. Broadly speaking, whatever I said here can be translated in terms to the terms of quantum mechanics, and so let me try just very broadly to relate to what you were saying. So in quantum mechanics, of course, without quantum mechanics, we cannot account for objects, etc. This is well known. So when I say that a microstate, by my definition, or the way that I see it, and there are good reasons to do so, when I say that a microstate is a complete description of the state, say, of the universe, then when I move to quantum mechanics, the microstate is the wave function of the entire, sorry?
It's then, excuse me, a question of how do you prepare the state?
Oh yes, yeah, there is, okay. So I'll start with just talking with this, without preparation and then add the preparation. So before I enter this, of course, the detail of preparation, then the microstate of the universe is its wave function, and it's not small at all. It's very big. It's the entire thing with the entanglement between, maybe the entire universe. So the microstate of the universe at a point of time is its wave function. It's very big. Now, if I want to prepare, what do I mean by preparing a system? Preparing a system is, to use rough terms, focusing my attention on part of the universe, tracing out the rest of it. And so the effective appearance of things is very different. We have improper mixtures and so on to describe those subsystems. But all of this is talk about the microstate of the universe. And quantum mechanics, viewed from this perspective, is a theory in which there is no statistical mechanics. It's micromechanics.
Who makes the claim that quantum mechanics applies to all of the universe?
Yes. The theory, the fundamental theory, this is what it's doing. Now, if we want to do statistical mechanics and we want to put in, for example, ignorance about the prepared state of a system, then we have to think very carefully about the notion of ignorance in quantum mechanics. And it's a very subtle notion. For example, in standard von Neumann formulation of quantum mechanics, when you measure a system, it collapses to a microstate. And there is no ignorance. There is complete notion, complete knowledge by definition of the outcome of the measurement. No ignorance remains. And it's a very complex thing to think about circumstances in which there is room for ignorance. We did that in a forthcoming paper, but I will not go into this. In Bohmian mechanics, there is, of course, room for ignorance and so on, but you have to look at the details to see if there is ignorance at all. Otherwise, it's microstates. It's the fundamental theory. No ignorance is involved, so it's not statistical mechanics in that sense. It's a very partial answer, but we can go on later.
Well, thank you. Very clear talk. I only missed the point. I have a question about that point and then a comment. The point is that you talked about in the previous slide of two probability measures,
Yes.
and both are empirically determined.
Yes.
But how do you know that they agree when you represent them in the phase space? I mean, usually we use the volume of the phase space, but how do we know in advance that they have to agree?
First of all, they don't. They don't have the entropy measure doesn't have this to be the same as the probability measure. Luckily, it happens to be the case that we can reasonably well work in the classical case with the Lebesgue measure and in the quantum case with the quantum measure. So it works, but if we want to explain why it works and where the measure comes from, and if the answer is not to be from some a priori principles of I don't know what, then this is the only way that I can explain.
Okay. So you are saying that when we learn that we apply a measure to a phase space, this is wrong. We should consider the two measures and let's see if they agree or not.
That's right. And often people say that formalism says apply uniform probability distribution relative to the Lebesgue measure on the initial macrostate and then evolve the dynamics. This works well if the measure is the Lebesgue measure, because then
Yes.
you can use the Lebesgue measure and then work backwards. And so if you after you found out that the correct measure is the Lebesgue measure, then you work backwards. And,
Yes, the
and
Liouville theorem.
It will be yes, you need a theorem, and if the Lebesgue measure is the right one, I think it can be shown that it's a good idea to describe or to give an algorithm for predictions in this way. But the algorithm is not the explanation of why the measure is as it is, because otherwise, why Lebesgue? We explain why Lebesgue, and we work then backwards, and then we can start again, but we have a good explanation of why this particular measure.
Okay, so I will left the comment for later.
Okay.
Okay, one last question.
Thank you. Thank you, Orly. It's a philosophical point. I'm not sure your criterion of existence and your criterion of description should go together the way you put them together. Because you say, microstates, we have a complete description, and you repeated many times that this is all that exists.
Yes.
This is everything there is, the microstate.
Yes.
And I think that the question of existence depends on the satisfaction of the reference relation. So I can refer to you as Orly Shenker, I can refer to you as the author of The Road, co-author of the Road to Maximus Demon, and as long as these descriptions are correct, your existence is ensured
Yes.
by the fact that you satisfy these descriptions.
Yes.
And neither of these descriptions is a complete description of you, obviously, fortunately, but they're still descriptions of you, and you exist. So it doesn't make sense to say nothing but the complete description of Orly Shenker. Orly Shenker exists.
Yes.
And it's the same for a physical system with a certain energy, with a certain temperature, exists or doesn't exist. It doesn't depend on our having a complete description or an incomplete description. So I don't think you can say nothing but the microstate exists.
So thank you. Perhaps I should say a bit more about the notion of description, which is, of course, is a word that is easy to use, convenient to use, but what I mean to say is something ontological. According to mechanics, this is what mechanics says, is that what there is the microstate. Now, and in that sense, if I'm referring to you as Yemima or the author of the book on conventionalism, then I'm using two macro variables, that is, two partial descriptions of you, and perhaps there are different people with the same name. I don't think with the same book, but people with the same name. And so if I only use the name, this will not be about you. I will not be able to infer anything about you, but only partially. I will say that you are a case of this. So I would say that these are macro variables. And you're correct that the term description should be treated with suspicion because it's actually an ontological claim. The full microstate is a claim about the ontology. The partial, the properties or a part of that thing which exists, an aspect, I would say, of that which exists, could be a matter of the description of somebody from outside and so on. But you are right that the word description should be treated with suspicion, and aspect would be a much better word about this. So yes, thank you for this. I think you're right about this.
Thank you.